All right, good afternoon, everyone. Good afternoon, Professor Allison. My name is Timothy Velasco. This is my partner, Sean Robinson. And today we present to you our MIPS 32 processor, the Havasu. So our purpose is to provide you guys insight into the MIPS instruction set architecture, which is the interface between the physical machine and the software superimposed on it. And always keep in mind the 4 design principles when you're designing, anything along these lines. I'll just run through our presentation overview. So we're going to cover the instruction set architecture and the 5 fundamentals behind that. We'll go into hardware design implementation, enhancements, and finally design verification. So to get started with the instruction set architecture, it is a Harvard memory architecture. It follows a reduced instruction set computer design. So what the Harvard memory is the separation of instruction and data memory, which allows us to fetch an instruction and read or write a result on the same clock. So that gives us a higher throughput, faster execution with simple instructions. Also, it's in a big endian format, so basically what that means is the data is transferred to memory, MSB first, as shown. And then we get into the register set of the MIPS machine. So there's 32 registers. Keep in mind the MIPS is word addressable. And these are predetermined registers, so the programmer's not going to have any control over these. This is just kind of a background thing going on. But major registers we'll be using later on is the stack pointer, maybe the 0. The data types of the MIPS processor, signed and unsigned. So signed values represent negative and positive values, and it's actually the default type for hardware description language like Verilog. It ranges from 0 to all Fs. And keep in mind that MSB is what determines the sign of the value. Now for unsigned, it doesn't account for negatives, but it allows the programmer to reach higher positive values. So same range, but all positive. All right, our instruction types. So there's 3 instruction types we use: register type, R type, immediate type, I type, and jump type, J type. So these are the binary formats for each of the following types. So this is the R type that's broken up into 6 separate fields. And what's special about the R type, obviously the opcode field, 31 to 26, is all zeros. That's how you know it's an R type. So you go down to your function to figure out what specific R type instruction you want to use. Now for the I type, the 31 to 26 are actually used. So you know it's an I type or a J type. And then you figure out what instruction it is, and then bits 15 to 0 are reserved for the immediate value. Finally, the J type, same thing. The opcode is in 31 to 26, but now bits 25 to 0 are used for address. So that's concatenated with the PC and 2-bit sign extension to a jump to an address. So there's 3 types of addressing modes we use in the MIPS machine. Immediate mode, register mode, and register indirect mode. And we'll go over some examples. So just a short example of immediate mode. You can use the instruction add immediate to add an immediate value of 1 to register T1, as shown here. So register T1 is getting a 1 added to it. Moving to register direct mode, this is more like R-type instructions. So for example, an add, you're adding a register to another register. So T2 and T1 are being added and stored into T0, as shown here. T0, T1, T2. And then finally we have register indirect mode. So good examples of instructions for this are maybe a load word or a store word. So as you can see, we go to the address of R7 right here in memory. We grab the data contents in that address, and then we load it into R6. These are all the R-type instructions we used for our MIPS machine. So opcode shown here. All the I-type and J-type instructions used. And I'll pass it over to Sean.
All right, now we're going to go over the hardware design implementation. This is our top-level design with the CPU, data memory, and I/O memory. This is our CPU unit with the control unit, the instruction unit, and the integer data path. Inside we have the instruction unit with the program counter, the instruction memory, the instruction register, and the sign extension. The program counter and the instruction register are 32-bit register values, or 32-bit registers that interact with the instruction memory. They both write operations in synchronous form. They both have high active loads, and the program counter has a high active PC in that increments by 4. And we also have the instruction memory that is big Indian format, 1K by 32 byte addressable memory. And with the sign extended 16, we have it concatenated with the MSB 16 bits of 0.
If it's 16-bit 0, that's not sign extension, right? That would be 0 fill,
Yeah, concatenation with a 0 fill, I'm sorry.
but that's not sign extension. You'd be wanting to replicate IR15 16 times.
Oh, okay.
That just does a 0 fill.
This is the integer data path. The integer data path has the register file, the RS and RT registers with the TMUX, the ALU module with high, low, ALU out, D in, and IO in registers, a YMUX, and some of the additional IDPs, or the additions in the IDP that we made is the SMUX rather, that accesses the S address of the register file and what we use for the stack pointer R29. Next we have the TMUX, which we have the data to RT from the register file. We have the immediate value from the IU, the program counter that we added in for stack pointers, and then the flags for the stack pointer control as well. Along with that, in the ALU level, we added a barrel shifter, so we added a shift amount into the ALU.
Mm-hmm.
This is our ALU. Inside our ALU, it brings in S data, T data, and the shift amount. We have multiply, divide, and MIPS operation modules, the ALU MUX, and the addition that we added was the shift left immediate, shift right immediate, shift right arithmetic barrel shifters inside the MIPS module. The enhancements. First we're going to start with the barrel shifter and with the example there at the bottom. So the way we did it was a case statement with the hex value of the shift amount, the overflows or don't cares for all of them. The carry for the shift left logical is the MSB. And then what we did here was the N is supposed to represent the decimal value of the shift amount. The next enhancement we did was an input. The input is an I-type instruction. And then this is the RTL for an input. For a I-type during the decode, RS gets the data from the register file, and RT gets that of the sign extent or the immediate value. On input 1, ALU out gets the contents of RS plus RT. Please note that this wire is also does have the data going in, but we do not access that data.
Mm-hmm.
Input 2, the IO register gets the contents that comes from the IO memory at ALU out address. And input 3, that data is then sent from the IO register out of the YMUX into the register file. Next, the next enhancement that we have is an output. The output is an I-type as well, with the RTL right here. Just like that of an input instruction on a decode, the RS gets it from the register file, and the RT gets it from the immediate. On an output 1, ALU out is RS is added with RT, and RT gets the contents from the register file into the RT register. That will be accessed on the next clock. Output 2, then takes that from the ALU out and goes into the IO memory, and the contents of RT goes into the address location in the IO memory.
Yeah.
Next, we have set interrupt enable, which is an R-type instruction. And this is our control word for it that changes the present and next state interrupt flag to 1, which is used inside here in order to trigger an interrupt. The interrupt here comes from the IO memory module, which is right here. On a reset, there's a delay that then makes this bit 1, which allows for an interrupt to occur.
Mm-hmm.
Next enhancement that we have is an interrupt. The reason for this slide is an interrupt can only occur during a fetch state as long as the interrupt acknowledges 0 and the interrupt is set high. So at first we had 11 states, and that was due to the fact that we wanted to initialize the stack pointer at 3FC. So the first 2 states sets R29 to that of the 3FC, and we realized that that will only allow our interrupt to have 1 stack pointer, or 1 interrupt. So
Wasn't the stack pointer specified to be initialized to 3FC a reset?
yeah, that was a mistake that we missed.
Oh, okay.
Which is fixed.
Yeah. So what we did was we were able to cut down the states for the interrupt to make it more generic, so we
So
can
you
have
picked
one.
that up, eventually you fixed it and
Yeah.
did do it, and, okay, got it. Yeah, that saves you those 2.
Yeah.
We
Good.
just wanted to go over the mistake made.
Yeah.
So in order to address the mistake, we wanted to show you guys here, and then these are the states that would be changed.
Full disclosure, huh?
Yeah. So it would turn out to be 8 states, not 11.
Yeah.
So I run through it real fast. So the R29 contents, which is the stack pointer contents, is then saved into RS. ALU out is incremented by 4 because we did a pre-inc stack pointer. And then RT gets the contents of the PC of the contents of the PC that was interrupted.
Are you about to push something? Just curious, you're about to push something? So you're
Yes.
getting ready to push?
Yeah,
So
we're about to push the program counter onto the stack.
So you incremented from 3FC to 400?
Yeah,
That's outside your memory range.
outside of our memory range.
Yeah, memory ends at 3FF. So you just bumped your stack pointer to, in essence, it would be 0 if you truncated the last 12 bits. We were supposed to decrement. So you would write to memory, but you'd be writing to memory location 0.
Okay.
So you did increment.
Yeah, we did.
Yeah, okay, so it would write,
Mhm.
and it would push and pop,
It did.
but it was pushing and popping on top of code.
We didn't have anything in.
Yeah, our code starts at 0.
We had it in memory. When we checked.
Oh,
the
that's right,
memory
this is
module.
gonna be data memory, not,
Yeah.
my bad, yeah. But keep going, so as long as we know that, you're gonna decrement on the pops.
Yeah.
Yeah,
Okay.
just keep going.
Post deck.
Yeah.
Next, the data from ALU out becomes the address of the data memory,
Got it.
and then the content in RT, which is the stack, or the program counter is saved into data memory at
That address.
0x400,
Yeah,
at least for the first one. Sorry, let me go back real fast. I want to show you as well that the ALU out is then also put into the register file back onto the stack pointer register. Next state, we do access it, right here.
mm-hmm,
We increment it again,
mm-hmm.
except this time for RT, we bring in the flags. We then push the flags onto the stack inside the data memory after we incremented it, and we save the contents of the new stack pointer value back into the register file.
Okay, so hold it right there. And this highlighting is excellent. I don't know if Tim did that or you did
I
it.
did.
It's excellent. But you say we're gonna put the flags into RT on the previous step?
Mm-hmm.
Yeah. Where are the flags coming from?
The AOU out.
Yeah, that's not what we push. You need to push your present state flag register. So those are combinational outputs. We can't push those.
Oh, okay.
You need to push the flags that are getting clocked every clock tick, and those are combinational outputs. That's not what we're supposed to push. So you needed to have a path in somehow to get to RT from where, I'm assuming your flags, present state flags register is in the control unit?
Mm-hmm.
Yeah, you needed a path from there to RT.
Oh, okay.
That's what you're supposed to push. So you did push something for sure, but
Yeah.
it wasn't the present state of the flags.
Okay.
It was whatever's coming out of the ALU at the time.
Yeah,
So you'll have to fix that next edition.
absolutely.
Okay, keep rolling.
So then we save the going to be changed flags into the data memory at the incremented state,
Mm-hmm.
or the incremented address. And then we save the stack pointer register, or the new stack pointer register back into the register file. And then we also push ALU, or we push 3FC into ALU out register. Next, then we take the 3FC and we access it in data memory, and we store it into, or we write it into the register DN,
Mhm.
data in. Then we take register DN and we, so this is the path, and this is what I wanted to point out as well. It would have made it a little clunky to have the PC in go to the PC mugs all the way around in the diagram, so I showed it over here. That we have it go back into the program counter. Next, we have the return with interrupts. I didn't add all the states into this one. It is in the reverse order that we push it on, so it's a post decrement. So we grab the contents of the stack pointer, put it in ALU out. We grab that location and put it into the data in register. We also re-grab the contents. We grab the flags. ALU out is then decremented.
So when you say ION,
Mm.
I think that should be DN, right?
Yeah, that I forgot to change that, I'm sorry.
And you say it goes to the flags. What flags does it go to?
We have, in our control word, we have the flags and it rewrites, or it writes over those.
So you did put it in there at that point.
Yeah, so the issue that we had was we did just take it from the flags themselves, but we added in, we concatenated in the zeros, so it was 32.
So you've got your DN register, right? DN.
Yeah,
And you have a path on the next clock to go from DN back into your control unit?
mm-hmm.
You do? You did that?
Yeah, I did put it on here, I'm sorry. That was it.
Okay, we'll check it out.
Oh, yeah, I'm sorry, yeah, it's this one here.
No, that's when you wrote it.
Yeah,
Yeah. That's not the present state flag.
I didn't put it, I put it in the line back. I'm sorry, I forgot.
But keep
one.
going, you're okay.
So then here, we decrement the stack pointer. It goes into, or we put the contents back into the stack pointer, because it's a post decrement.
Mm-hmm.
And then we grab the stack pointer value, ALU out, put the data, which is now the program counter, onto the DN register. We load in the stack pointer. The program counter is then, or the program in counter at the program mugs brings in the stored program counter,
Yeah.
and we decrement the stack pointer, which takes us back to the original stack pointer.
All right, we go over a little bit of the design verification. So we used, obviously, the instruction memory modules that you provided to us, Professor Allison. So we'll start with module 13, and this is verifying our interrupt service routine without the use of the stack pointer. So started off, obviously registers 1 through 7 are initialized with these values, and then we start conducting add operations, right? And then once we hit interrupt service routine, we'll jump down to the loop, which, well, these are also initialized. So register 16 is going to be the memory pointer that is decremented throughout the loop. So we can store our data into the I/O memory. And then register 18 is going to be our loop counter, which will also decrement. So we should loop 16 times, as shown here. And the data is changing in register 17, and that's what's actually being stored into I/O memory.
All right.
So yeah, so if we run through it, we use the output instruction. We output the contents of register 17 into our first memory location. We change the contents of register 17. We increment the memory pointer, and then we decrement the loop counter. And that runs through until the loop is complete. We reset the memory pointer back to the original location, and we use the input instruction to input the contents of this memory back into our registers 19 through 24.
Excellent. Great slide.
Now for module 14, we're actually going to use the stack pointer. So basically the same concept. Registers 1 through 7 are initialized with Louis Ories. We start conducting add operations until we hit interrupt service routine. The registers are initialized the same way, the memory pointer, the loop counter. But this time, once we complete the loop, we should jump back to the location set by the stack pointer to leave off on the instructions to go back to the instruction we last left off at before we entered the interrupt service routine.
Which is that 1C, address 1C.
Yeah. And that's it.